controversial.
Thank you.
Take it away.
So usually when I present some experimental results on using remote viewing to predict the stock market, or the cybotic stuff that I talked about last time, using Psi for practical purposes. This time, I'm going to be talking about a pet peeve about quantum mechanics. And this is something that isn't just my pet peeve, because as soon as I put out the title of the talk, quite a few people came and said, yeah, that needs to be said again. So I'm not saying anything breakthrough or very dramatic, but I'm just saying something that a lot of us have been thinking. So quantum mechanics has been invoked for all sorts of things. One thing is in my lab. My lab is called the Quantum Engineering Lab, and we use quantum mechanics to produce little widgets that do things based on quantum principles. But quantum mechanics has also been invoked for healing. Does it really involve healing? And once you're healing, why not quantum sleep? And once you're doing that, why not toothpaste? Once you're doing that, wait a minute, a spa? Ice cream? Quantum real estate management? Quantum restaurant and bar? These are all real things. Quantum auto sales? They must be very little cars. Quantum construction? Now this is really getting silly. Quantum sealant? Can it get any lower than this? Yes, it can. Quantum toilets. So I'm not going to be talking about any of those. What I want to talk about is quantum as applied to Psi. And so quantum has been invoked in Psi for several different applications and several different approaches. Two dominant ways are one is the observer effect, which I'll talk about for psychokinesis and wave function collapse. And the second is entanglement for non-local information transfer. At the end, I'll also talk about the inverse, and that is how Psi might be used in quantum mechanics. So let's talk about psychokinesis. We all know about that, where we have some sort of a random system that's fundamentally random. It could be rolling dice, flipping a coin, an electronic random number generator. We use intention, and the intention gives rise to an effect that goes in the direction of intention. So the question is that a quantum effect? And it has been interpreted as a quantum effect for quite a while. And this is the observer effect, where in quantum mechanics you have a wave function which is in a superposition of different states. It collapses to a single state when it's observed. But traditional quantum mechanics calls that a detection perspective. However, there are some deviating views. The ones that are known best are from von Neumann and Wigner, who interpreted it as being the consciousness collapses the wave function and gives you this specific state, that essentially every system can be looked at subsumed in another system until you get to consciousness, and at that point, consciousness collapses the wave function. Wigner wrote, "The quantum description of objects is influenced by impressions entering my consciousnness." And this has been applied to Psi research by a number of different people. Helmut Schmidt did it, Evan Harris Walker, Stapp, Hout Cooper, and a number of others. And so the question is, does this really work? And so if you take a look here at an experiment by Schmidt. So in this experiment, Schmidt pre-recorded some random information and then afterwards had an observer observe the information with the intention of driving it in a certain direction. And then he had another observer observe it again. And so the data that goes up, which shows essentially the cumulative deviation as the number of runs, the data that goes up is where a strongly Psi successful observer observed the data and intended it to go up. Then later, a non-successful Psi observer looked at it and it didn't affect it. The curve that does not go up, the bottom one, is where the unsuccessful Psi observer first observed it. So Schmidt interprets this as sort of a collapse of a wave function. Once it's in a particular state, then it can no longer be affected even if somebody else looks at it again. And This has been repeated in various sorts of forms. One repetition was by Biermann in 2006, and he found an unsuccessful replication. Others have found some successful replications in various forms. Really, the classic case is Schrödinger's cat. Schrödinger proposed this to show how absurd the observer effect was, but it's actually been taken as the opposite, as an example of how the observer effect could work, where you've got a cat in a closed capsule with a vial, and that vial releases a poisonous gas or not, depending on a quantum mechanical random process. And the idea is that the cat is in an indeterminate state until you open the vial, look at it, and at that point, the cat will have been dead for a certain amount of time or will be alive or not. So it's in a cat state. It's now actually called that. And so this is an idea of, again, observation creating a collapse of a wave function. Another example that's commonly invoked is the Young's double slit experiment. So in the double slit experiment, we've got light going through two slits. Because of the path difference between these two slits, you either get constructive or destructive interference of the waves on a screen behind it. And so you end up with a set of fringes. This is a classic experiment. Where it becomes quantum mechanical is when you bring it down to an extremely low intensity where you just have one photon at a time coming through. And at that point, you still get the double slit experiment, but you can't know which slit the photon went through. If you put a detector there to measure which slit the photon went through, the effect goes away. So that's also interpreted as a measurement makes the effect go away, makes the indeterminacy, the wave-like properties, go away. Now, this has been carried through to various psi experiments. And Dean Radin talked about some of his experiments. He's done the most extensive array of experiments, but others have done some too. At the Pear Lab, Ibison and Jeffers and others have done these experiments. And so this is, I pulled some data from a 2012 paper. And in this data, what you see is the fringe visibility as a function of sample. And so here there are some observers or some meditators. And so they concentrate on the apparatus periodically. When they concentrate on the apparatus, the visibility goes down, meaning that this effect seems to disappear, and so there seems to be this kind of observer effect, because they may not even be intending the visibility to go down. All they're doing is essentially imposing their concentration and consciousness on this. And the effect works, and you see something. Now, is this, in fact, a quantum observer effect? So we see the collapse of the quantum wave function from conscious observation. In the double slit experiment, the observer or detector can cause only one direction of effect. In other words, if you observe it, you're going to see a reduction in visibility of the fringes. On the other hand, we also see this sort of effect in other types of experiments, such as dice, coin flips, random number generators, where we can bias the output in one direction or another. That's no longer possibly the quantum observer effect. There you're actually applying an intention that pushes it in one direction or another. So how do we know that the double slit is a conscious observer effect and that the dice aren't? To me, they look very much the same. And the intention of the experimenter and the people looking at the effect is for the collapse of the wave function or for the double slit experiment to produce what you want it to produce. And so it does. So does this demonstrate the collapse of the quantum wave function? Is there some sort of a unique response that shows that it is uniquely a quantum mechanical behavior as opposed to just our usual, quote unquote, psychokinetic behavior where we apply an intention to a random system and it manifests? Or are we simply acting on any random system the way that psi acts on any random system? We carried out an experiment earlier in 2007 at the University of Colorado where we had an incandescent light source going through a piece of glass to two detectors. And so part of the light was reflected, part is transmitted, and we had observers trying to either increase the amount of transmission or decrease the amount of transmission using their intention. And in fact, it worked, and we got, depending on how you look at it, some statistically significant results. And it's been replicated, but we never really did this in a deep way. This is very much like the other sorts of experiments, but here we're biasing it in a direction. We're not just turning it on and off using our intention. So I would say here, is this due to conscious collapse of a wave function? Hell if I know. I really can't tell, and you can't, there's no signature here. Yes, you do something and it works, but what is it due to? I don't know. So is consciousness collapse of the wave function accepted physics? Absolutely not. It's a minority of physicists who would take the von Neumann-Wigner approach. And in fact, there are other quantum mechanical formulations and other interpretations that don't even need a conscious observer effect, that don't even need an observer effect at all. Stochastic electrodynamics, which is a pet theory that I like quite a bit, that's based on zero-point energy fluctuations, doesn't need an observer effect. Cramer's transactional interpretation, which is a beautiful description of a much more intuitively acceptable description of the standard mathematics of quantum mechanics rather than the Copenhagen interpretation. It doesn't have an observer. You just have a forward-going wave and a backward-going wave. They make a transaction. And in fact, in general, other people have said this. Bierman more recently said all you need is time reversal. You don't need any sort of observer effect. So let's take a look at another case here, and that has to do with information transfer. And so I said that I was going to talk about quantum entanglement as the second thing. So we know that there's telepathy for a long, long time. I show here a picture of Upton Sinclair's book in which he describes transmission of images from himself to his wife, who was in another room or another building, and she drew them. And if you haven't looked at this book, look at it. It's just amazing. Then there's also remote viewing or clairvoyance. Here we have an example of a person who was in the Stargate project, and he happens to be sitting in this room as well. He doesn't look like that anymore. He doesn't have any hair now. Or we have the example of Daryl Bem's premonitions experiment, which are very robustly show some sort of these effects. So quantum entanglement has been invoked as a possible mechanism here. Let's talk about quantum entanglement. The easiest way to talk about quantum entanglement is with the EPR experiment. So that's the Einstein-Podolsky-Rosen experiment, in which Einstein proposed the idea to show how silly it was, a little bit like Schrödinger with his cat. And so the basic idea here is we have a source, shown as the red object in the middle. And this is a random source that sends out two particles in opposite directions. Let's call them photons. And these two photons are linked because by the conservation of momentum, they have to have complementary, that's not, complementing, let me put it that way, polarizations to preserve momentum. So if you on one side, on the left side, have a polarizer that's up-down, and you measure that the photon goes through, then if on the other side you have a polarizer that would let the allowed other particle to come through, you also will find that it goes through 100% of the time. If you then rotate the polarizer on the left to some other angle, then you change the statistics of whether the light is going to come through the polarizer on the right-hand side. And so there is this sort of effect where you've got action at a distance, and it's instantaneous over as much distance as you want. However, it's correlation. It's not causation. There's no communication of information. How do we know? because in each case, since this is a random source that's producing these things, there's a 50% chance that the light is going to go through each polarizer no matter which way you orient the polarizers. And so it's only after the experiment is done and you go to the left-hand side and say, did it go through here? Then you can correlate it with, oh yes, it went through here on the right-hand side. That's correlation, it's not causation, and it's due to the randomness of the source. So then I would say that actually I should stay here for a sec, that this cannot be used in the case of, for example, a mother waking up in the night and saying, oh no, my son is in trouble, when her son over in a distant city had a car accident. There's genuine information transfer. Now you can argue that there's a sort of a correlation, global correlational effect and so on. Yeah, you can do this, but you're really making a pretty complex model at that point. So if we take a look at the invocation of quantum mechanics to psi phenomena, let's take a look at what the Pair Lab has done. So they have always been very careful to invoke quantum mechanics as an analogy, not saying that this is due to quantum mechanics. Or you take Dean Radin's book on entangled minds, which I still use as the textbook for my course on psi. He's very careful to say that entanglement is not signal transfer, that it's only correlations, and you need some other ingredient if you're going to view this as a mechanism for information transfer. So in fact, what I'm arguing against is the loose use of quantum mechanics in the vernacular with regard to psi phenomena. Now we can turn this around, by the way, and this is how psi concepts apply to quantum mechanics. If we take randomness, so random decay, where you've got some quantum mechanical thing decaying at a random time, you say it's quantum mechanically fundamentally random. But most of us in this room know that that ain't true, that in fact we can use intention to affect the randomness of something and that it's not random. Essentially, intention, if you like, is a hidden variable, although I think there are other ways to describe it. So in fact, psi phenomena definitely does show an issue and modify quantum mechanics. Another case is retrocausality and entanglement. So this was described by a student of de Broglie, Costa de Beauregard, in the mid-20th century, and then Charles Lear at the SSE has written a couple of papers on it as well. Basically the idea, and here's the same slide again with quantum entanglement, if you take a look at that source and say the source sends something out to the left, you rotate that polarizer. Now, if that rotation of the polarizer then is transmitted backwards in time to the source so that the source can now send out an encoded photon to the right-hand side, then you're using retrocausation to get rid of action at a distance. You're getting retrocausation to get rid of this spooky effect, and it makes so much sense. Everything all of a sudden falls into place with this explanation. I came across a video of Costa de Beauregard and another physicist talking about this. It was on YouTube, and I just came across it a couple of months ago. And the interviewer asked them, why has this not entered the mainstream of quantum mechanics? It's a much more clean explanation than the muddy Copenhagen interpretation. And de Beauregard, and what they said is the reason it hasn't is that if you introduce retrocausality into physics, it opens the door to parapsychology. And the physics community doesn't want to hear about that. I found that amusing. Okay, so there is a real need in psi for theoretical foundations. We're really lacking it. However, when we are looking for models, let's look, rather than for global models that are very loose, let's look for precise models that are testable, where we can use Poplar's falsifiability approach. If we don't have something that has quantitative predictions that we can falsify, then we haven't said anything at all. And what I'm asking for, gasp, is reductionism. And I know that's a dirty word in our community because we take a holistic approach. But don't throw out the baby with the bathwater. There are times to use a reductionist approach as well, to make precise models that give us pieces of what's happening that we can then build up. Thank you.
Please explain to me how you can have an experiment that doesn't eventually have an observer, no matter how far removed. So I don't quite understand how you can have, you can say there's no observer effect at some indeterminate time.
Thank you for asking it that. So yes, I agree with you. If we ever know about that experiment, it most certainly has an observer. What I'm saying is that we don't know that it's the observer effect that caused the psychokinesis to occur in a certain direction. There's no particular signature of that versus just intention causes a random thing to happen the way we want.
Hey, I didn't think that was so controversial, but I thought it was really cool. And I wanted to say, Hugh Price and I can't remember the name, wrote that, that recent article about cost.
Yes.
They're basically
it's
trying
a
to
beautiful
It's a beautiful article, right? Anyway, I emailed Hugh Price and I said, so if you think about it, this opens the door for retrocausal communication.
What was his response?
He said, no, I don't, no. And I said, yeah, it does. And then he didn't respond. So, but I just wanted to mirror that I had that same experience of like, please don't say that.
Yes.
Because he didn't have an actual response that was, legitimate.
Yeah. It's just sort of an allergy to talking about anything that might open the door.
So I just wanted to point out something that people occasionally lose track of. I agree that quantum theory as we have it is not really an explanation to psi phenomena, because even if wave function collapse is producing the effects, there is nothing in QM that allows you to bias the collapse in a favored direction. However, quantum theory, for all its beauty and power, is a theory. On the other hand, EPR correlations have been experimentally observed. They're facts. They're not going to go away even if some genius comes up with a replacement for quantum theory tomorrow. And this is why I, at least, frequently find myself thinking that whatever connection underlies the EPR type correlations may be very important to how psi works, even though it's not explained by quantum theory.
Fully accepted, and we really need to invoke those sort of correlations more precisely in our theory.
Thanks, Garret, for a very thoughtful talk, and I would probably 85% agree with you, because I think we need to be really careful about extrapolating physical facts into the macro world. But I think one point I would like to point out is that quantum theory is not just a physical theory. It is a physical theory, but you can use the basic structure, as we have done in our generalized version, to produce a systemic theory that is applicable to systems that have similar or, say, isomorphic structures to quantum systems. And whenever that happens, you can do that, and then you predict, as we have shown, a generalized form of entanglement which may be able to explain at least some of the phenomena. And the point here is the basic element of every quantum formalism is the handling of non-commuting or incompatible operations, as you know. And I think if you look at consciousness, we have here the prime example of a system for which you need a formalism that can handle incompatible operations, or, put differently, a formalism that can handle a situation where the measurement changes the state of the system. And the prime system is consciousness, because whenever you measure consciousness, you change the state of the system. So I think there is a case here to extrapolate not quantum theory or quantum physics, but the formalism of quantum theory to other systems. And I think that needs to be said. That's why I'm here.
Good, thank you. I guess a question, and maybe this is for later discussion, is when you're generalizing it like this, is it quantum mechanics or is it an analogy of quantum
No,
mechanics?
it's not quantum mechanics. It's a general quantum theory.
Okay, good.
That's what I want to say.
Good.
And therefore, I think you're both right and 15% not.
Okay, thank you. So let's collapse the wave function one way or the other, right?
Hey, Garret, I just wanted to thank you for your presentation, and I hope there are ways you can shout it from the mountaintop a little bit more. I'm not a scientist, I'm a practitioner and experiencer, and I know that there's something cultural and psychological about how practitioners try and think about what it is they're doing. Imagine right now the word Zen is breathing a sigh of relief saying the word quantum can take over. You know, like that'll, because when we try and think about what we're doing while we're doing it, it has an effect on the effect or how well we can do it. And I know so many young psychics are developing themselves, and if they're off reading too many quantum books, it's affecting how well they actually do and how they develop as human beings. So this, I breathe a sigh of relief. I'm like, thank God I can stop studying quantum theory and just get back to doing what comes
Right.
naturally
Right.
without analyzing too much. So thanks.
Thank you.
Thank you, Garret.